All right. Hello there, everyone. I'm having a little bit of issues here with my video. I don't know. Can anyone see my video? Please put it in the chat if you can. Yes. Okay, good. Good, good, good. All right. Well, for some reason, I can't see myself on video. Oh, you can see me, but not my screen. Okay, so let's make sure the screen sharing is working. All right. Okay, good. I am screen sharing. Screen is okay, just no terminal. Okay, can people see the screen now? Good now? Okay, good. All right, thanks everyone. Little technology issues this morning. Okay, cool. So let me bring up my notes here. We'll get started. I think didn't get a ton of questions over the last week, but one question that did come up had to do with the RM package and how that works and what it's all about. And just to sort of recap those discussions, RM is basically keeping track of all the packages or the extra software that you're using for your project. And this sort of encapsulates things and puts it inside your project as opposed to hiding it away somewhere on your computer where you can't find it. This is something that is, I guess, strongly recommended, but not critical for what you're doing. If it causes you too many problems, it's not something that you have to work with. If you try to use the templates and the functions, in particular, easy install from the Blazor templates package, that should help smooth out some of the issues, at least that I've encountered with RM. So try to use it, but don't let it inhibit you from what you're trying to get done. Yeah, let me know if you have any other questions, and let's get started. So today I want to actually do one more thing to go back to last week. One important point that I realized we didn't cover adequately was on factors. And factors are another data type. So we did talk about characters. We talked about doubles or numeric values. We talked a little bit maybe about integers. Integers are just what they sound like. They're integers. But factors are really important to understand because you want to always understand if you're dealing with a string, a character string, or a factor. And a factor is basically an integer bound to a character string. And so it's more of like it's treated as an integer, but it's actually displayed on your screen. And in any sort of a figure or any sort of a table you might make, it's displayed as a character. So it's a little bit confusing, and it's a little bit hidden, but you want to understand when that's happening. And R will tell you when it's treating something as a factor. So you just want to pay attention to that. And just to give you a quick demonstration on what factors are, I'm just going to go into my RStudio workshop project here and show you. And I just started a new session. So as a reminder, we're always going to, when we start a new session, we're going to source our dependencies file, and that's going to load up all of the packages that we need. And we're going to source the configs file, and that's going to make all the sort of settings that we want to have. And then we can close those because those are done for the day. And if we go to here now, week 3, we'll just start up here and I'll show you. This is how you create a factor in R. It's basically, you know, the word factor and then a character vector. And then if you want to, you can explicitly state what order you want the factors to come in. And if I run this, you'll see that it returns A, B, and C, which is the same thing that you put into here, but that the levels are C, B, and A. And you know, R has this sort of default behavior of basically you know, alphabetizing character strings and alphabetizing factors based on the alphabetical order. And that may not be what you want for your figure or for something else. And this is actually how you change the order of things to get away from the default order that R imposes on you. So that is mostly when you're going to be using factors, is to change the order of, say, variables or values, however you want to think of it in your plots. And I'll show you, you know, sort of how that comes into play later on when we get into plots today. Okay, so that's factors. All right, so the main theme for today is about functions, okay? But before I want to talk about functions, I'm going to say, so why do you want to like be thinking about functions? And really, functions, if you can use functions in your programming, in your analysis, it's going to help you avoid errors. And this is really why you want to use it. It's going to save you time and it's going to help you avoid errors. And so there are a number of ways that we've already talked about in order to prevent errors in your analysis. Okay, one that we talked about last week was to use pipes to avoid saving intermediate values. So if you're doing a number of different manipulations on a piece of data, then you can either save that value after each step, or you can use a pipe to immediately carry it over to the next step. And that, you know, the less sort of intermediate values you have hanging around in your global environment or the memory for your session, you know, the better off you're going to be, and less likely that's going to get confused later on. For things that you do have to save, you can use unique and informative variable names. You know, so like avoid using X to save things that you really have to save. And then today we're going to talk about using functional programming techniques. And so that's really an important technique for you, I think, to understand if you're going to be working in R. And then the last bit here is to use prepackaged processed data. And that's something we're going to get to in the last lecture. And that's going to keep your data separate from your coding, so that, and that's going to help you prevent you getting confused with what you're working with. So today we're talking about functional programming techniques, which is really just a fancy word. And there's a lot of fancy words today, or a lot of like computer science type words today. And I don't want you to get confused or, you know, get bogged down in the terminology. But basically a function is a set of instructions for the computer to transform one piece of data or one value or one set of values into another set of values. So you have your input and you have your output. You know, the way you are going to tell the computer what to do is the way you're going to tell the computer what to do is by providing arguments to the function, okay? And so this is an example of how you would do that, okay? And I'm gonna go, this is on your notes, and so you can find this on the website, but I have it here in the script for today. So a very simple function that you can create here is a function that's gonna add two values, okay? And these are called the arguments here. This is the command that tells R that you're creating a function, okay? And that function is assigned to a name that you can create. In this case, function name is not a great name. I would call it like, my sum or something like that. So if you're just adding two numbers, but this is how it's structured. So you have the name that's going to be assigned to the function, this special word here, function, that tells R that you're making a function, any arguments that you want to provide for it, any values that you want to provide as input for the function. All of the code or instructions that you're going to have the function do is going to be inside these curly braces here, okay? These little brackets here, curly brackets. And so that's all the instructions here. And you can have one line or many lines inside the function. And then usually at the end, you're going to want to put a return statement, okay? And this is going to be what the function puts out back into either the console, or you can assign the value of that function to a new variable, okay? There are different ways you can write this sort of a thing. There's shortcuts. These shortcuts, by and large, I find to be confusing and unnecessary. And so I want you all to try and write your functions this way, and it will be very easy when you're going back and trying to see what you did 3-6 months ago or a year ago, exactly what is a function and what is returning at the end. So always use this sort of a format when you're writing your functions in R, okay? And I can just show you how this works. So if we run this, that will now assign in our global environment here. Let me just make this a little bit bigger for you. This now assigns to the value, or to the name, function name, the value of this function, okay? So it's now a set of instructions under the name, function name, within our global environment, okay? So that hasn't returned anything to the console because we haven't run the function yet. And so in order to run the function, you're going to just type the name of the function, and you're going to provide the arguments that it requires, okay? So if I now run this, it's going to return that value to the console down here. 1 + 2 is 3, okay? I can also, if I choose, assign this to a value, say result, okay, would be, this here, okay? And that will put result into my global environment, okay? So hopefully that is pretty clear how that works. That's a basic function. Okay, so so the thing that's going to protect you, or to make your analysis more robust and error-proof, is the concept of scope. And so scope is simply, I've written it here for you, is a set of name-value relationships, okay? And we've already spoken about this in lecture 1 when we talked about packages and environments. But today it's going to be, something that we're going to work with more, because when you're working in R, functions create their own scope or environment. You can think of it sort of either way. And this is helpful because when we talked about, using like X for a variable name, or result or something like that, which is sort of ambiguous and you might want to use in different circumstances. What you can do when you're working inside of a function is you can reuse those things as many times as you want, and they're never going to be overwritten, or you're never going to be confused because they stay local inside the body of the function. Okay, so I have an example here that hopefully will point this out. And first of all, already what we are referring to when we talk about scope. Okay, so if we look over here in the global environment, we have this word result, and result is sort of a, not a great variable name to use because it's kind of ambiguous and you might want to use it again. And let's say that, we have another function that's going to return a result. In this case, that result is 5. Okay, and so if I run this, now result has changed from 3 to 5 here in my global environment. And that's because all of this was happening in the same scope of this global environment. So that's the sort of thing that we want to avoid. And here's how we avoid that. We can make this function here, and this function we're going to call good sum. The function we initiate or instantiate with this word here, function. It's going to have 2 arguments, add in 1, add in 2. That's going to return a result. So this is basically the same thing that we wrote up here. And so that's a good way to make a sum. Okay, so if we run good sum, 1 plus 2, that's going to equal 3. And so what R has done is when we say, all right, run this function, it creates a little mini environment, a little micro environment, which is transient, which only exists while that function is being run. And so even though we had already used the, maybe we had already used the arguments add in 1 or add in 2 or something like that previously or in a different function, it doesn't matter because this is in its own little world. And that's going to keep you from confusing your values when you're doing a series of analyses. Okay, so that's a good way to do it. So now R is not as you know, I'm sure it's not always going to be error proof or function in the sort of most reliable way. So you want to be aware of situations where you can get in trouble, okay? And I provide an example here. So this we're going to call bad sum. And in this case, we've only provided add in 2 as the only argument for this. Well, how do you add just like a single value? Well, that doesn't really make sense. So, but R, kind of has a default behavior where let's say we tell it to look for add in 1. Now, add in 1 is not within the scope of this function because we haven't provided it as a named argument when we define the function. Okay, so it says, all right, add in 1, it's not there. I don't know what it is. It's a variable. It's not like pi or something that I already know. So let's look outside of this little environment here to the next environment up. And usually the next environment up when you're writing a function like this is going to be the global environment. So it's going to go into the global environment and look for add in 1. And if it can find it, it's going to use it. Okay. If it can't find it, it will return an error. I can't find, add in 1. Okay. So let me show you an example of a bad way to write a function. Okay. So this is bad sum. And if I haven't defined add in 1 here, so I'll just, skip over that for now. If I run bad sum add in 2, it's going to give me an error. And it says down here, object add in 1 is not found. Okay, so that's like, a helpful error, and that tells us that we've written our function wrong. But what can happen is that if you've got add in 1 sitting now in your environment here, so now add in 1 is a value in our global environment, now it's actually going to be available for R to go after. And so it's now found add in 1 in our global environment. It's gone up a level and found it, and now it's taken add in 1 and added it to add in 2. And so that's actually a behavior that we don't want R to be doing. There's no way to turn that off automatically, as far as I know. So you always want to, when you're writing your functions, always be certain, or always try as best you can to explicitly more or less import the values that you want as arguments. And that way they're strictly going to be used within that scope of that function. Okay. So, and you can see here, why this is, this is a very powerful concept, because if I go back to good sum and I have add in 1 here, and add in 1 is, in the global environment, it's 2, but here I'm, setting it to 3. And so if I run this now, what's going to happen is R is going to look for addend1. It's going to be provided within the scope, and it's going to ignore. It's not even going to look for addend1 in the global environment. So if I run this, it should return 5, and there it is. Okay, so so that's an example of functional programming techniques, and this is a very simple, basic example, but it can apply to very complex functions that you anything that you want to construct. Okay, another point to make is, we've, as we've described it here, we've been returning explicitly like a single value. Okay, so you can't return like result 1, result 2, result 3 as separate values in R. You can only return a single value, out of a function. But what you can do is you can actually combine multiple values into a list, or it doesn't have to be a list. It can be a vector that you can return if you want to do that. But let's say you wanted to return a table and a plot and a value of some sort. Well, you can put all those things together inside of a list and return the list as a single element. So that's how you get around this sort of limitation of only returning a single value. And I can demonstrate that here. So here we have a function that will calculate 2 averages. All right, so it's going to calculate the mean, calculate the median. It's going to put those into a list that we're going to call return list. It will provide names to that list. So this is helpful because maybe we don't, when we come back to this value, we won't remember which one is first and which one's second. So let's put names on them. So that will name them, and it will return that list as a solitary, single object. Okay. So here's 2 averages, and it's going to take in X here, and X is this vector of values. And if I run 2 averages, it's returned a list here, and the mean is 3.1 and the median is 3. Okay. So that's a very flexible way to return whatever it is that you want to return from your function. All right. Next topic to discuss is not strictly applicable only to functions, but is a way that's going to make your functions more powerful. And this is conditional statements and basically if-else statements. And this is going to provide some logic for your functions, so that maybe you want to catch some errors or some unhelpful conditions that might come up in your when you're analyzing your data, like say a 0 or a missing value. These things are always causing problems. So you might want to catch those with a conditional statement. You might want to do anything else that you can imagine, actually. So if-else statements are really important to know, and especially inside of functions. So so let's go here, and let's just demonstrate how we can use if-else statements to protect a function from returning unhelpful or confusing values. Okay, so in this case, we'll call this unsafe divide, and all it does, it takes 2 numbers, x and y, and it divides them. Okay, and returns that result. All right, so I can run unsafe divide, and that creates the function. Now, if I run unsafe divide with y equals 0, we're dividing by 0, and you were probably taught in math class that you can't do that. R, for some reason, assigns infinity to that value. Infinity is not a useful answer for us, so we want to catch that and maybe like fix it somehow. You could say replace it if you wanted to, or you could just let's say return a message that tells you that you're trying to do something that's not good. So we have a function here. Now what we've done is we're testing if the denominator, in this case y, is equal to 0, you're going to do one thing, else you're going to do another thing. Okay, and so the way this is structured, you're always going to have the if, a space, and then a conditional test. And the result of this conditional test should be a single value, true or false. And the simplest way to demonstrate it is, does a number equal another number, or Does a value equal another value, or is it greater than or less than? These are the simplest type of conditional tests that you can use, but you can use others. So then you're going to have like these curly braces, all right? And that's like what happens if, if true, and if false or else, you can do what happens in the second curly braces here, okay? Now you don't have to have an else statement. You can just say, all right, if y equals 0, do this, and then go on to the next thing. If that was what you wanted to do, you could say, all right, print the warning, says you're trying to divide by 0, this is not recommended, and then just give the infinity result if you wanted to do that. So basically, the else statement will only happen in the case where this is false, that sort of thing. So if I run this now, we have safe divide. We try and divide by 0. It says you can't divide by 0. Okay, so that's it on. All right, here's a question. You have elif in R. Well, yeah. So like else if, it's not really written like that. There is another thing. There's like a more concise form called if else that you can do, which is a nice way to go. And so the way if else works is you can do. Let's see if I can do it. It's a little bit hard for me to do this on the fly, but the way it works is you say if else. And then you would put the text of your test in here. So you would say y equals 0, and then you would say, what you do if yes. So you'll say you can't divide. Okay, and then no, you say return x. So result. Yeah, then we'd say x divided by y is the way you do that. Okay. Anyways, so that's a more concise way that you can write that. All right. So, but to sort of get back to this question here, the elif statement, you can you can put another if here. All right, so that's the way you do that, else if, and then you have to put another test there, and then you would do another brace there, that sort of thing. So that's how you construct an elif statement. Good question. All right, so next topic that is what we want to talk about is mapping, okay? And so you're going to use map to apply your function to a vector or list of values. Now, why would you want to do this? Well, so when I took like my first computer programming class, which was in middle school, I think, and then I didn't take any computer programming for probably 20 years. You learn how to do like an iteration statement. So for like say I equals 1 to 10, do this, that sort of thing. So that's one way to do iteration. It's one way to like repeatedly, do a command. And that's great because that is the computer doing things that you don't have to copy and paste or type out multiple times. Because, as you get older, at least as I get older, like I can't copy and paste, I can't retype things multiple times without making mistakes. And so you want to use clever ways to have the computer do that for you. Iteration using a for loop is one way to do it. Now, why are we not talking about for loops? Why are we talking about this other thing called map? Well, for loops are good, but the main problem is that they tend to operate in the global environment. So they operate in the scope that you're doing everything else in. So if you were to create multiple intermediate values or variables in your for loop, those things would get created and recreated every time. And it's possible that that's gonna cause problems with other things that you're trying to do in your analysis script. So the for loops, that's the primary reason that for loops are suboptimal. Another reason is that they are difficult to parallelize. So If you're working on a very complicated, long calculation, and that's not something we're going to talk about in detail, it's much easier to parallelize a map command. Map commands can also be faster if you're doing, hundreds of thousands of iterations, which sometimes you might have to do. So we're not going to talk about for loops. If you want to look into them, I mean, if there may be cases where you need to use them. So what map is a functional, which is a function that takes another function as an argument. Okay. And what it's going to do, it takes only, in its basic form, it takes only two arguments. The first argument is either a vector or a list, so a collection of objects that will be then supplied to your function, which is the second argument, as the arguments. And it will do this in turn. It will start with the first value, put that into your function and generate a result. And then we'll take the second value, put that into the function and generate a result. And all this is happening, using functions. So the scope of your function is, is what's defined by the function. It's not in the global environment. And that's, like I said, it's going to protect you from making mistakes. Okay, so let's demonstrate how this works. Now, the map that I'm using here, I think is a little bit easier to use than the base version of map, which comes with R. So this map comes from the PURRR package. Okay, and that, if you're working along with this workshop project, you've already installed tidyverse with this this command here, library tidyverse. Okay. So that will install this per package for you. All right, and I think that's the recommended way to go. It's much easier to use. So very simply, let's say we wanted to generate a function that adds 1 to a vector, adds 1 to a value. Okay, very simple. All of the values that we want to use are here. That's .x. Okay, so we're going to ultimately add 1 to 1, 2, and 3. The function is here. .f is a function of x, and within and just like we defined functions previously, that's going to, all the code and stuff is going to go inside these curly braces. And so what's going to happen here is we're going to add x, which in this case is going to be 1, 2, or 3. We're going to add that to 1, and that's going to be the result. And we're going to return the result. Okay, so I can just run this, and it should run by itself. And what we've done here is we've returned a list. So map, as its base function, returns a list of values, 2, 3, and 4. That's 1 plus 1, 2, and 3. Okay, so that's very simply how you're going to use a map functional. Okay, there are multiple variations on a theme, and this is why I think one of the reasons why this version of map is more useful than the base version. Well, because maybe you don't want a list, maybe you want like a vector. Okay, that seems like it would be more useful, maybe. So in this case, you can use map double, and that will return the values as a numeric vector. Okay, and so if I run this, all the stuff in here is the same. I've just added this underscore DBL. Now, if I run this, it will return the thing as a numeric vector. Okay. Okay, so does map simply create a list? If so, why not just use the list command? Outstanding question. Okay, so the answer is that you definitely do not need to use map for this simple of a calculation. Okay, it's much more straightforward. It's much faster, computationally, to simply use vector math. So you can say, and we talked about this before, 1 plus 1, 2, and 3. That's going to give you the same result. And you can't sense the difference now, but like if you're doing that a million times, it would be much, much faster to do it that way rather than to use the mapping command. I'm just trying to show you, as an example, like how to construct the map sort of concept. And the reason why, you might have to use map is because if you're doing more complicated things or more complicated calculations that don't fit, into a vector or use vectorized operations like addition, then like you have to know how to do that. So, but that's an outstanding question. So you could either use list or or vectorized math to do the same sort of thing in this case. All right. So now this is where it's starting to get a little more complicated, because now we're going to add some text to what we want to return, and we can use multiple different arguments. In this case, we can use map2. And what map2 will do is allow us to put in 2 values that we're going to map along. And it will take the first value of x, the first value of y, and we'll plop them here into our function f. Okay. And this x here has to match up with this dot x, and this y has to match up with this dot y. And we'll say, all right, we'll make the result. Result is x plus 1, and it's going to return a paste, which is you're going to take the value and stick them together into a character vector. It's going to paste this text and then the result together. Okay. So the first result is 2, second result is 3, the final result is 4. Okay. So that's good. But maybe you want to map along an arbitrary list of values. Okay, let's say you had 4 or 5 different things that you wanted to sort of plop into your function and then iterate through all those in order. Well, you can use this thing here called pmap. It stands for parallel map. And in this case, there's only 2 arguments. The first argument is a list here, .l, and then you have the same, very similar function down here for .f. And what .l is going to be a list, and the elements of the list are going to be whatever you want in there. So x, beginning text, and an end text. Our function has to have those same arguments here, x, begin text, and end text. And we'll take the first of x, and we'll take the first beginning text, and we'll take the first of the end text. We'll plop all those into our function, and it will return the result. Okay, and this will return, in this case, a list. If you are doing mathematical, numerical calculations, you could have it return like a numeric vector or anything else. So the underscore doubles also applies to pmap. Okay, so if I run this, we get the first result is 2 apples and then 3 bananas and 4 cherries. Okay, so that's how you can map across an arbitrary. There's basically no limit to the number of things that you can map across in parallel. They just have to, basically be in order. They have to be in the same order. And so one way that's really convenient to do this is to have a data frame or a tibble with all of the parameters that you wanted to map across, and then extract each one of those using like your $sign. So instead of 1, 2, and 3, maybe we'll say, your argument tibble, and we'll say x, for example. And then so it'll go down that. And then so your beginning text would be, say, argument tibble. So hopefully that's clear how you can use that. Okay, so that is functional programming. Now, I wanted to now switch gears a little bit and talk about plotting. Okay, and this is a really important part of what we do. If you're running a lab, or if you're working in a lab, or working on your PhD or your postdoc, you're going to be taking your data, you're going to do statistical testing on it, and you're going to put it into a figure. And so this is, how you're going to do that in R. So we'll start with some example data, and someone asked actually over the past week about example data. There's like a ton of example data sets in R that you can play around with, and I'll just actually take a second here to highlight those. So if you look at the data sets package, these are all the different data sets that are available for you that are just like built in with your R distribution. So these just come with it. And so in this case, we're going to use Iris, but you can, you can look at any of these. And if you, run, F1, that will bring up the help page, and you can then scroll through all the different data sets here in your help page. Okay, so we're going to just use the regular Iris data set, for our example today. This is very similar to what we worked with last week. So those are our data. Now, the approach that we're going to take is using a program or a package called ggplot. And the concept here is you're going to build a figure, a plot, a panel by layers. And the layers you're going to add sort of come in different categories. And there's no like official documentation about how to set this up and arrange it. But you want to have like an approach that you use as a sort of a habit. And I'll show you my recommended approach. But this will help you keep your stuff more organized. And so when you go back and you want to change something, you know exactly where to look every time. Okay. So the initial thing you want to do, that you have to do when you're building a ggplot, is you have to develop, or you have to establish the framework, is what I call it, for the plot. And this is sort of like the underlying data structure that holds your data that you're gonna from the table that you're gonna basically plot from. And it holds what we call mapping values or aesthetics. And the aesthetic, an aesthetic in the concept of ggplot has a formal concept, and that is a relationship between a visual parameter and a piece of your data. Okay, so in this case, we'll just show you the data is Iris, and I just printed out the data here. So this is just the table that we're going to be working from. And the mapping is going to be, in this case, assigning the column species, which in this case is a factor, as we talked about, to the x-axis, and then sepal length, which is a numeric value here, to the y-axis. Okay, so that's what we're going to plot. We're going to plot the sepal length by species. Okay, and that's like probably the most common thing, or the most basic thing that you're going to be doing with your lab data, is having experimental groups and plotting a numeric value for each group. Okay, X and Y are not the only aesthetics. We'll show you more as we go through, but you can use fill, color, size, alpha, or transparency. So there are, multiple ways we can show 5 or 6 dimensions in total of our data using these different aesthetics. So an aesthetic is how you basically visualize a dimension of your data, and it's a very powerful way. It can be combined in very powerful ways to show a lot of information. Okay, so we'll run this, and it basically doesn't do anything. And if you look down here to this plot, it's basically set up the framework for the plot, but we haven't added any instructions for how to display the actual data. Okay, and so the first thing that I do when I'm building a ggplot is I'm going to put what's called a geom in, and a geom is like a shape, and a shape like an icon or something like that. You can have a bar or a column or points, these sorts of things. So in this case, we're going to add what's called a jitter. All right, and a jitter plot is nice. It sort of adds a little bit of random noise to each of the points. So it's not all stacked up together. So that makes a nice, pretty clear representation of the differences between these groups. Okay. There are lots of geoms. At the end, I'm going to show you some resources for, how to find different types of plots that you might want to make. I think for, common lab data, geom jitter is a good way to go. Okay. We can add some additional aesthetics, okay? And in this case, what I'm showing here, it's the same data, same X and Y aesthetics. Now we're gonna make the color assigned according to the species, okay? So it's gonna put each of these points into a different color. And the fill, which is like sort of the internal coloring of the point rather than the outline. So color is the outline, fill is the sort of the internal coloring. And so it's going to assign those according to these values. So they're going to be mapped to data now. We're going to use the same geom. And in this case, we're going to change the shape. There's a whole panel of ggplot shapes that I'll show you at the end. So 21 is good. It's a circle with a center, which is a different color, or can be a different color. Alpha is a transparency value for the center, and size is just the size of the point, okay? So if I run that, now you can see we've got, you know, some points, and they're in nice different colors, and we've got a legend here, and the legend is generated because now we've added these additional aesthetic parameters here, okay? Next thing that you might, you know, or should want to do is to add some measure of central tendency and variation. So like a mean and a standard error. Now, the way that you're going to do this is with this command here called stat summary. And this is a little bit sort of, you know, not entirely clear from what's written here, what's going on. But what this is doing is it's taking this particular function, and this function is basically built into ggplot, so you don't have to create this function, but it's taking this function, it's applying it to your data, and then it's returning some values. And you don't really get to interact with those values, but those values are the mean plus or minus the standard error, okay? And it's gonna turn those into, in this case, what's called a crossbar. It's going to make it black, and it's going to make the, you know, sort of the filling of that with an alpha of 0.2. Now you can change all this stuff if you want. This is what I usually use though, okay? And this is the order I usually build up these plots in. I usually will put the geom, one or more geoms first, and then I'll do like this sort of error bars here, okay? So that's what you get there. There is the mean plus or minus the standard error for each of these guys, okay? Now, one thing I always hated about, you know, before I discovered this particular package is putting in the little stars and stuff to show significance. And, you know, a lot of journals like that. Some journals like maybe they don't like that, but you know, you're going to want to do at some point like a t-test or a Wilcoxon test on your data to see if things are significantly different or not, okay? And you know, working in R can be like very tedious not to have some help to do that. So if you use this package, ggpub-r, it's very helpful, and they, you know, have this function here that you can add to compare the means. And it's very, very logical. You say, all right, I want to use a t-test. The label is going to be the p signif. That just means like the stars. And then the comparisons, these are going to be the little brackets that tell you what the pairwise comparisons are. And this comes in the form of a list with all the different comparisons as sort of 2 vector elements for this list. Okay, so this is going to now add a new layer to our plot with significant stars using the basically a Welch's t-test, and it's going to make comparisons between these two, and these two. Okay, I've already run the library command, so we can skip that. And so here's what we get. So now we get the nice, you know, significant stars. You can also have this print out the actual value if you're interested in that. Yeah, so that's something that most people want to have on their figures. Okay, cool. So now the next thing is, you know, you may sort of like not like the default colors that are put in. You know, for the different groups. So in order to change that, you're going to use scales. Okay, And scales are how you change the aesthetic parameters of the aesthetics. Okay, so and there I used aesthetics twice in different senses, but the aesthetics in this case, if you're going to change the color, the values of the colors that you're going to use to plot, or the values of the fill color, or let's say the range of the x-axis or the range of the y-axis, or the size of the points if you're mapping size as an aesthetic for your data. So scale is the command that you use to change all those things. And usually, R does a good job with the X and Y axes. I don't really, usually change those too much, but, oftentimes I want to change the color to make them, sort of consistent across a number of different plots. Okay, so in this case, we use the scale fill. Scale fill brewer comes as a separate package, but basically gets loaded automatically with tidyverse. This is a nice set of color palettes that I'll show you in a second. Yeah, so you just pick a palette, and you tell it what aesthetics you want to apply it to, the fill, and in this case, the fill and the color. So if I run that, you get now some nice new colors. Okay, so where did I get these values from? So let's just go here. We'll just do a little bit of Googling. So our color brewer. This is what you want here, the first value, or first hit on Google. And so these are the R color brewer palettes. So you have some nice options here for, sort of one-sided gradient colors, for discrete color values. In this case, we're plotting categorical data, so we use the dark 2 just to get as different of values as possible. And you have some nice palettes here for two-ended sort of gradients. So like, say, for a heat map, for a gene expression heat map, that sort of thing. So these are always like, good options to go for in terms of colors, and they're automatically, brought in with this scale fill brewer or scale color brewer command. Okay, so after I get the colors set, the next thing that we, so here's another thing to point out actually, is that, we don't have to sort of, restrict ourselves to the pre-packaged colors. You can actually, pick different colors. And in this case, we can manually assign colors to each of these values here, and you use the scale fill manual command to do that. Okay. In this case, we have red 3, green 4, blue 3. Okay, so that's the scale fill manual. And if you want to have a nice summary of the let's see here. This one here is a good. And so these are all the different colors that R can generate. It's a little bit small, I realize, on your screen, but so this is like basically every color that's defined in R. So that's another good way to choose colors by hand if that's what you want to do. All right. Next, so one thing about this plot is, I don't like this gray background. I think it looks kind of weird. Some people might like it, but we can actually use what's called a theme, and the theme changes like the very sort of the look of your plots, and it changes it. I like to use a pre-packaged theme because it keeps it consistent with the minimum number of commands that you have to fill in, because you can manually change the size of all these things here. You can change the size or the color of these numbers or the ticks. You can put axes in and change the weight of the axes, but like, why do you want to do all that? So the best way to do it is to use this pre-packaged theme here called theme cowplot. And I think that's just the best way to go. So I've already loaded this, but you're going to want to make sure you install and load the cowplot package. And then, you just put this line down here, this theme cowplot, that will make it look nice. And in this case, I don't think we really need the legend because it doesn't really help us. We already know what all these different groups are. It's quite obvious. So we can get rid of the legend using that command there. Okay, so that looks pretty good. And yeah, so that's basically how you build up a set of commands for a ggplot. You start with your framework, you add the geoms, and in my opinion, you should then add the sort of statistical sort of values, you know, the mean and the standard error, the statistical tests. Then I do like the purely sort of visual, you know, aesthetic, you know, that sort of thing. Okay. So sorry, what does cowplot do to ggplot? All right, so the only thing that cowplot does is that it provides this theme. It automatically sets the panel to be white or transparent, I guess. It sets the name, you know, the axis names to be a certain size and a certain font. It sets the axes lines to be a certain color, in this case black, and a certain weight. So all these things, are just like totally graphic and aesthetic sort of parameters for your plot. So it makes it look nice and consistent across all the things that you're trying to plot. Okay, so we have 5 minutes left. I want to show you a couple of other things here on statistical testing that you're going to find important. And one of these is, you know, how to do like a t-test. Okay, and this was in your exercises for last week. But what I want to show you is, so this is how you would do like a t-test using the base, the normal function of R, the t-test. And I think this is, I mean, this totally works. So I can run this and you get like this text here, and the text is like very like verbose, and it's got a lot of, you know, it's kind of hard to get these values out of here. You have to know what you're doing more or less, but you can, yeah, you can see the mean, and you can get the p-value here, so that's great. But I think it's just like not ideal. And this text up here is kind of difficult to like understand what you're trying to get there. But that's how you would do a t-test between these two groups using the regular t-test function. What I prefer actually is this package here, rstatics, and what that will do is that actually will simplify it so that you can actually just use the pipe notation in order to get a t-test according to group. Okay, and so I'll skip this for a second, but so this is how you would do the exact same thing. Okay, and so here what you've got is, I'll just bring it up here. Here what you've got is a t-test according, you know, between the on the sepal length value according to species. So you get the same thing here, except it's much more concise, and it's returned it into a nice, useful table for you here. And so you can see, you know, the setosa versus versicolor. You know, you got the p value and an adjusted p value as well, which is always good to have. Okay, so that's the way I'd recommend doing your statistical testing. You know, you can do a Wilcox test that way, all the simple stuff that you would normally do for your experiments. This other command here, that will actually give you a nice set of summary statistics for all of the values in your table, the min, max, median, et cetera, et cetera, et cetera. So that's a nice way to get like a full statistical breakdown of your data. So I'd recommend that as well. Brad, can these packages be easily applied on Seurat output? Yeah, more or less. So definitely cowplot you can. And cowplot, I think, is something that in the Seurat vignettes is like basically you're going to load that to begin with anyways. Most, you know, Seurat, Monocle, a lot of these other things, they often use that because it looks nice. Yeah, our statistics, yeah. I mean, if you're getting like some tabular data out of cowplot, out of Seurat, then yeah, you can totally use that on Seurat as well. So that's no problem. Okay, I'm going to take just a couple seconds here. Now, what I'm going to do is I'm going to put links to all these tabs up here into the notes for the day, so you don't have to worry about that. But let me just show you some other things, some other resources that are going to be useful for you. So you can go to, I want to show you the ggplot cheat sheet. And that's how I usually get to this stuff, is by Googling it, RStudio cheat sheets. And then, yeah, you can go here and and that will download the cheat sheet for you. And this shows you all of the different sort of geoms that you can use, like a column or a box plot, a violin plot, these sorts of things. Here it shows you the crossbar that I use, but you can also use error bars and line range, these sorts of things for the plus or minus standard error. So definitely use this cheat sheet here. The other thing I wanted to point out for you is in the notes for today on the sort of the main website is this book here. It's called Our Graphics Cookbook. This has a ton of different ways for you to create a line graph if you want. It will tell you exactly, how to plot this with ggplot or a scatter plot. So this is like how you plot anything that you ever want to plot in R or ggplot. So this is like the sort of master cookbook if you want to find out how to make a specific plot. The other thing you can always do, of course, is Google. Google's going to tell you, you say Google like bar plot, ggplot, and that will find it for you. The other thing I want to show you is we can go back here. Actually, is we can go to if we go to the PURRR cheat sheet. You want that one here. This is also a good one. This tells you about how all the different options you have for I don't know what's not downloading. There we go. This shows you different options you have for the map commands to, use a double, return a double, return an integer, return a character vector, these sorts of things. So this is a good sort of resource that I use all the time as well. All right, last question before we go for the day. Can we use the factors to identify the cells co-expressing two or more genes? That's a complicated question. We can get to that in a couple of weeks when we talk about the single cell stuff. All right, so we're at the end of the day today. So thanks for hanging in there, guys. I will update the website with these links for you. Check out the video. Definitely go to the issues section and post any issues that you're going to have. Have a great week. And we're going to be back in 2 weeks. So we're going to have next week off. We'll be back in 2 weeks. And we're going to start working on the single cell stuff. All right. Take care, everyone. Thanks.